Coffee on the stove heating up from this morning. And today we're going to do some linear algebra. We're going to do the subspaces exercises. The subspaces exercises. Let me get my phone set up to read the chat on my phone as I do. Stream Manager. All right, I had some new followers. Very nice. Yeah, there's a lot of followers. 45 already. Wow. Almost to 50 followers, everybody. So we got to do some math here. We're going to do some pen and paper. We're going to do some pen and paper. Hold on. There's one person I was going to text about my stream. Because they said they were also working on linear algebra done right. Still 0 viewers. I'm going to take a slow start. Wait for there to be a viewer or two. But ultimately, we're going to do these exercises. There's like 20 of them. There is quite a few subspace exercises. There's 24 subspace exercises. I did a few of them. I did this one. I did number 2. I did number 3. I just did 1, 2, and 3. I don't think I did. Yeah, I didn't do 4. So I'm going to have to start with 4, and I'm just going to knock out these exercises, baby. We're going to knock them out. Now, let me see if this coffee's ready. Nope. All right. It was 5 seconds from being ready, and I walked away. Hot coffee. Hot cup of COFFE. Here we go. Show that, suppose B is in R. Show that the set of continuous real-valued functions f on the interval 0, 1 such that the integral from 0 to 1 of f equals b it's a subspace. So the set of functions such that this condition is a subspace of R to the 0, 1, meaning function from 0, 1 into R, if and only if b is equal to 0. If and only if b is equal to 0, everybody. So let me just erase everything on my screen. Some of it's not erasing. I'm going to have to do another new screen because some of it's just not erasing. Why do you think this isn't erasing? It doesn't erase the eraser either. So I'm just going to have to do Command New. Don't save. Okay. Here we go. Now we're at the beginning. So we have B is an R. F is a C infinity. Meaning I'm assuming it's a C infinity. It might be like a once differentiable function or something like that. Right? But it's... No, wait. It didn't say differentiable. It said continuous. No, it says continuous. It says continuous. Because continuous functions are integrable. So we don't have C infinity. continuous of f is a hypothesis, H1. H1 is that f is continuous. Oh, you know what? I didn't tweet about the stream. Let me go to my Twitter followers real quick because I forgot to tweet about the stream. Starting stream now. Twitch.tv/ And the other hypothesis, no, f isn't from R into R. F is from 0, 1 into R. And f is continuous. And the hypothesis I'm doing the forward direction first. Integral from 0 to 1 of f equals b. Forward direction implies well, no, it's such that the continuous functions on f such that this holds is a subspace of continuous functions from 0, 1 into R. If and only if b equals 0. So there's going to be two directions. I'm going to need a better notation in order to handle this. I really don't like this exercise. I don't like it because I don't know it. But I also don't like it because it deals with like analysis stuff that I don't feel like getting into. Viewers flipped from like 0 to 1 back to 0. That's fun. Um, Y'all, what the heck is the answer to this question? All right, we're going to do the forward direction. I don't like the way I set this up at all. Let's do something a little slightly more casual. We're talking about and squiggle from 0 to 1 of f equals b is a subspace of 0, 1. If and only if b equals 0. What's up, viewer? How's it going? Good to see you on the stream. Let me know in the chat how you're doing today. We are solving this exercise. All right, this is still this is still not casual enough. I want to go completely casual, like an analysis class. Like, get rid of this deductive crap. Like, let's just go like analysis style proofs. So like that, like the way it's written. And we're just doing the forward direction for now. Set of continuous real valued functions f on the interval. Let f in R01 be continuous and such that squiggle from 0 to 1 of f equals b. For b in R. We want to show that if functions f form a subspace of R to the 0, 1, then b equals 0. So, 1, additivity. Let fg be continuous R, damn it, be continuous R01 such that F plus squiggle 01G equals B plus B equals B. I mean, you see how, because it's closed under addition, right? So that means here, what I really mean to say is this. This is going to be great. We're going to show that 2B equals B, and the only way 2B can equal B is if B equals 0. That's not an ampersand. And squiggle from 0 to 1 of G equals B. Be continuous. So additivity. Let F and G be continuous 0, 1 into R such that squiggle from 0 to 1 of F equals B and squiggle 0 to 1 of G equals B. We want to show that squiggle of F plus G 0, 1 equals B. But squiggle 0, 1 of F plus G equals squiggle 0, 1 of F plus squiggle 0, 1 of G, which equals B plus B. Now, two B equals B implies that B equals 0. So you know what? I think we've proven the forward case using just additivity, and we don't have to use homogeneity. Not homogeneity, but scalativity. Homogeneity is the linear map thing, but additivity is also the linear map thing. But you know what I mean? Closed under addition. I don't mean additivity. I mean closed under addition. And using closed under addition, we already found that B has to be equal 0. So like the scaling case wouldn't show it actually. The scaling case wouldn't show it because squiggle KF 0 to 1 equals B. No, squiggle, this also shows it. So, 2, closed under scaling. Let F be continuous R1 such that squiggle equals B. Let K in R. If we multiply both sides by K, we get squiggle 1, we get K squiggle 1 F equals KB. But we distribute in, not really distribute, but we pull the K into the squiggle. KB, contradiction, not contradiction. If it's a linear, then it's not. Contradiction unless B equals 0. All right, so I'm satisfied with the former case. What's up, viewer number 2? Good to see you. Thanks for joining the stream. I am satisfied with the forward case of this proof. We're going to do the backwards case. See, I didn't want to do this. I looked at this proof. I said, I do not want to do that. And then what did I do? I thought about it for 5 minutes. And that's all it took, baby. Maybe it was like 10 minutes. But you know what? We thought about it for 5 minutes, and that's what it's really all about. That's what it's really all about. We're just out here thinking about math. So I'm going to delete the forward case because I'm fully satisfied with it. I'm fully satisfied with it. I could... Where is my... Yeah, here it is. I'm doing problem 4. This is chapter 1.c. Chapter 1.c, subspaces, and exercise number 4. I just want to check real quick. All right, baby. Deleting the forward case because we did it. What's the backwards case? The backwards case is let the set of functions f be determined by of functions f in continuous from 0, 1 to r be determined by squiggle 0, 1 f equals 0. Show that functions f are a subspace of r to the 0, 1. So this is easy. Oh, I didn't really check the 0 case. But logically, like it was like the additive case, the scaling case, the zero thing implies W. And like one of the conjuncts imposed a requirement on, since one of the conjuncts imposed a requirement on B, then that you have to use that requirement regardless of the other conjuncts. So I only had to show one conjunct. But really the forward case should have used like the 0 thing, the fact that the 0 has to be in the space. Well, which is true because of the 0 constant function equals B if and only if B equals 0. I mean, that's pretty trivial. Well, no, that's not true because squiggle zero constant function equals k for any k in R. And that k could equal b. So you actually don't have to. I don't think that the zero case is sufficient on its own. The additive case is sufficient on its own. The scaling case is sufficient on its own. But anyway, that's back in the forward case. Let's come back to the backward case. Additivity, respecting of addition. Let f and g be in the continuous functions from 0, 1 into R, such that squiggle f from 0 to 1 equals 0, and squiggle g 0 to 1 equals 0. Then squiggle f 0 to 1 plus squiggle g 0 to 1 equals 0 plus 0. Squiggle f plus g 0 to 1 equals 0. Check. Additivity, check. Scalativity. Let f be a continuous function from 0, 1 into R such that squiggle, the integral, when I say squiggle, I mean integral of f from 0 to 1 equals 0, and k is in R. If we multiply both sides by k, we get k squiggle 0, 1 f equals k0 equals squiggle kf 0 to 1 equals 0. Check. And then we have to show that squiggle 0, 1 of the 0 constant function equals 0. Which is true, I mean, basically by inspection. I mean, no, it's not true. Hold on, this is nonsense. I think this is in like the within epsilon of nonsense that like we can get away with it. But isn't the integral of the constant function a constant? The integral of the constant function 0 is the integral of a constant function 0 is a constant. The integral of a constant is k times x. Or x goes to k times x. But this I'm not so sure about. I'm satisfied with the exercise. I want to move on. I want to like keep up some sort of momentum through these exercises. So I'm gonna move on, but that was pretty satisfying. I didn't want to do it, but I'm glad I did it. Is R2 a subspace of the complex vector space C2? Yes. It is a subspace because, like, taking a vector space and fixing particular elements to 0, yeah, this is obviously true. I don't feel like proving this. This is obviously true because you're just fixing the ith component of the left and the ith component of the right. The imaginary part of each complex number in C2 set each imaginary part to 0. Yeah, 5 is trivial. 5 we're not going to spend time with. I was just looking at 6 and I was like, whoa, 6. So my intuition is telling me that a cubed equals b cubed is not like a linear relationship. And that equation does not express a linear relationship, so it's not going to be a subspace. That's my intuition. But proving it would be quite something. I should practice writing proofs anytime my intuition believes that it's right anyway. Hold on, I'm gonna go into a Discord room. There's a particular Discord room that I wanted to plug my stream in. Alright. What is going on? A cubed equals b cubed is a subspace of R3. I'm going to have to go back into the text to find a proof strategy here. I need to reread the text because there's something about representing vector spaces as sums of subspaces, and I have to remember the relationship between sum and direct sum. Is a cubed equals b cubed a subspace of R3? My feeling is no. And I don't know enough about complex numbers to know the answer to the third one, to the one about C. Yeah, I don't think. I already verified those. I verified those last week. Conditions for a subspace. Okay, let's try. Let's try it this way. Let's actually try it this way and see what we get. So we know that the zero vector is in the set ABC in R3 such that a cubed equals b cubed. That's true because 0 cubed equals 0 cubed. Check. Okay, so we have the first condition of a subspace. Yo, Gerhard, how we doing? Good to see you. Missed you last week. So I'm actually doing pen and paper today. I think most of today is going to be pen and paper because there's literally 24 exercises. And so what happened was I read the subspace chapter, and preliminarily, just like my hypothesis is that I'm going to have to break out of type classes in order to represent subspaces, right? So I'm going to have to go into records and ensembles, usually ensembles, to do subspaces. And today I'm doing the exercises pen and paper because there's 24 exercises. I don't want to skip them, and I need to sort of build up an intuition for what the proofs are going to look like before I try to formalize. So it's a pen and paper day here on the Linear Algebra Done Right in Cock stream. Maybe not any Cock today, but I did manage to push to GitHub. It turned out to be a thing with the Emacs shell. So you can check out what we did last week. There was just a lot of proofs. We made a lot of progress last week. But yeah, what was I doing? I'm going to show additivity. I'm going to attempt to show and possibly fail that let U, V each be in the set of A, B, C in R3 such that A cubed equals B cubed. U1 cubed equals U2 cubed. V1 cubed equals V3 cubed. We want to show that U1 plus U2, U1 plus V1 cubed equals U2. Wait, what? U1 plus U2, that's a 2. U2 plus V2 cubed. Okay, and I think this is a simple proof because what I'm going to do is I'm just going to observe that U1 cubed plus V1 cubed equals U2 cubed plus V2 cubed, and I'm going to basically assert that that's not derivable. Yeah, this is not derivable from this. It's true in special cases. But that's probably, you know what though? It's probably some freaking Olympiad problem to name all the vectors for which this is true or something like that. I don't know. It's probably not as bad as an Olympiad problem, but I feel like I'm satisfied just asserting this. Asserting that this is not derivable from this. Got a couple meetings and deadlines? Oh, the cube equals cube implies... That is true. Oh my gosh, that's so true. And that's why it's going to be not a subspace in R, but it is going to be a subspace in C. Where would I be without my viewers? It might help first to prove that x cubed equals y cubed implies that x equals y. Oh my gosh, this is going to be a subspace. This is going to be a subspace. The suspense is killing me. Cube root it's just AAC. No, you're 100% right. It's going to turn out to just be AAC. So if I do plus V1 on both sides, I get U1 plus V1 equals U2 plus V2, but U2 equals U1. Well, no, but V1, I'm sorry, U2 plus V1, but V1 equals V2. Then cube Gerhard, I was so wrong. I was like so wrong. I don't believe how wrong I was. I mean, I can kind of believe how wrong I was, but it's a diagonal 2D plane in 3D. I think I buy that. I think I more or less buy that. All right, so additive case. So we got 0 and we have addition. Now we need to check scalar multiplication. Let K in R. U1 cubed equals U2 cubed. Want to show that KU1 cubed equals KU2 cubed. So I think what we're going to do is we're going to do the same thing. We're going to take the cube root, multiply by K, and take the cube. We're done. It's a vector space. We have proven it's a vector space. We proved the addition case, the respecting addition case. We proved the respecting we proved the respecting addition case, we proved the respecting scaling case, and we proved that 0 is in. So now so the question, is this a subspace of R3? The answer is yes, and we've proven it. Now, is this going to be a subspace of C3? Is it a subspace of C3? The answer is going to be no, because cube root is not deterministic in C. The answer is no, because cube root is not deterministic in C. Now, how do you prove that? Cube root is not deterministic in C. And V1 cubed equals V2 cubed. Want to show that U1 plus V1 cubed equals U2 plus V2 cubed. Not going to be able to show because the cube root is not deterministic in C. Can I just say that, like, since, like, this would not fly in, like, a deductive context, but, like, it would fly, like, on this, like, on, like, an exam, at least the way, like, this analysis professor I had seemed to grade his exams. He never actually graded my exams because I wasn't registered for his course. I was just going to his lectures. But, like, his style of proofs, I think, would have accepted since cube root is not unique. I'll say unique instead of deterministic. In C, we can't show this. It doesn't fly in deduction, but it does fly in math. So I'm thinking I'm going to move on from this and just say that since I disproved the addition respecting case, that I'm done. Yeah, I'm done. I'm calling it. What's next? Give an example of a non-empty subset U of R2, such that U is closed under addition and undertaking additive inverses, but is not a subspace of R2. Ooh. It's closed under addition, but we don't necessarily have... Well, we do necessarily have 0, because if it's closed under additive inverses, and if it's closed under addition, then U minus U is 0, which is in U. So, so it does have the 0, it just doesn't respect scaling. And the next example is the dual of that. Alright, so I gotta be creative here. Oh. Let's think about it for 5 minutes before we panic. Before we complain and before we panic, we'll think about it for 5 minutes. So it's 2:49. So I'm going to panic and complain at 2:54. What could be a subspace that respects a subset of a vector space that respects addition but does not respect scaling? A subset of the vector space that respects addition but does not respect scaling. It respects addition, but does not respect scaling. I just gotta start writing down some subsets. Like, three Z is a subset of R. Oh, you're right. Damn! Ah, you should have let me struggle. It's not even 2:51. I was supposed to struggle for 5 minutes. All right, so we're talking about 3Z. That's a sigma. How do you type a Z? What direction does a Z go in? It goes like this. 3Z equals the set 3Z such that Z is in Z. One. Well, I don't need to check 0. I only need to do check addition. I need to check addition. I need to disprove scaling. Yeah, I mean, it's fine. Look, I need help, but like, I can't do this alone. But like, I should at least struggle for 5 minutes. But you're 100% right about this. I'm just going through the motions of checking it. I already know you're right. Let A be in 3Z. Want to show that A plus B in 3Z. Well, we know that there exists a KL in Z such that A equals 3K and B equals 3L. If we add these together, we get A plus B equals 3K plus 3L, and integers have distributivity because they're a field. So we have addition to not scalar mults. Let A be in 3Z as above. Let K in Z. Or you know what? We don't even have to, like, we have to think a little bit about like arithmetic in order to provide the correct witness if we let K and Z, but you said as a subset of R. It's much easier as a subset of R. So if we say let K equals pi, and then want to show that pi A is in 3Z, pi A is not in 3Z. All right. Well, we're still on schedule because all right, we're talking about now we're talking about the converse. We're talking about closed under scalar mults, but not under addition. Closed under scalar mult, but not under addition. Close under scale up, but not under addition. Okay, it's 2:50. It's 2:55. So at 3 o'clock, we're gonna start panicking and complaining about this. At 3 o'clock. So let me think outside the box. Let me think a little bit creative. Should I think about C? Should I think about a subset of C? A subset that respects scaling but does not respect addition. I'm thinking about in my head. I'm thinking about things I could do with C, about things I could do with R. Well, at first, if it respects scaling, does that necessarily mean it has 0 in it? That's a good question. If there's a way to do it in R2, if it respects scaling, does that mean if it respects scaling, does that automatically mean it has the 0 in it? For all f in U, U is a subset of V. For all f in U, for all k in, and let's just say that the underlying vector field is f, does question mark. Yes, it does. It does because 0 can be our special case of k. When k equals 0, 0f is still in U, which implies that 0 is in U. Okay, so it's not going to be enough to we have to break addition. We have to break addition. It's almost 3 o'clock. We respect scaling, but we break addition. All right, I'm just going to focus my efforts onto R2. I'm going to try to think of something in R2. R2, like a comma a squared does not respect scaling, I don't think. Yeah, it doesn't respect scaling. A comma a squared doesn't. Does does this. Equals minus x2. Let me just try this. The hint is that the scaling means you have the whole line included, so think about the two of those. All right, thanks. Thanks for the hint. I'll see you later. And let Knar want to show this trivially respects scaling. Yeah, this trivially respects scaling. So let me see if it respects addition. It probably does respect addition. I don't have like an intuition. I'm not like trying to think ahead. I'm just waiting until I verify it. Yeah, this is going to be fine. This is no. Of course, this respects addition. This is x plus y equals 0, which obviously respects addition. Scaling means you have a whole line included. Scaling means you have a whole line included. What does that mean? Let's erase this because it's clearly not going to work. What subset includes a whole line but does not respect addition? Oh! It's not just any y equals mx plus b, though. So if we did a equals x, y, and R2 such that y equals x or y equals x squared. That's not going to work either because that doesn't respect scaling. Because you would destruct this into two cases and the right case wouldn't work if you were trying to prove that it respected scaling. What am I not seeing? Is it just AA? Let U, V, and A want to show that U plus V is in A. Let me try this. This is gonna respect both scaling and addition. This is gonna respect addition, right? Because x plus x equals y plus y. If this is gonna respect addition. But what we can do is we can do this. A plus 1 such that A is an R. Subset of R2. Want to show is not in R. And KU. Not in R, but in A. u1 equals u2 minus 1, right? Yep. v1 equals v2 minus 1. u1 plus v1 equals u2 minus 1 plus v2 minus 1 equals u1 plus v1 minus 2. Does not equal u1 plus v1 minus 1. Ah! Wait. This is gonna break scaling. We've broken addition, which is awesome, which is what we wanted to do. Now we need to check if scaling breaks. U1 equals U2. No, scaling breaks too. Does not equal KU2 minus 1. So this is good for none of them. All right, it's 3:12. I said I was going to panic and complain at 12 minutes ago. But I have a hint. I literally have a hint. I should be able to get this. Ugh. It does not respect addition, but it does respect scaling. It does not respect addition, but it does respect scaling. It's going to be something with like sine and cosine. It better not be. Section 1.c skipped 8. All right, I've recorded that we skipped 8, and I'm moving on to 9 because it's been 15 minutes. It's been 20 minutes. I mean, 20 minutes isn't that long to think about an exercise, but like I want to try to keep moving and come back to stuff. Oh, great. Is the periodic functions from R to R a subspace of R to the R? I have a little bit of ladr. Alright, we're taking bets. Oh, you're back already. The axes are an example? Oh, x-axis, union y-axis? I thought of that. I thought of that. I thought of a union, but I thought of the wrong union. The union I thought of was y equals x or y equals x squared, which was dumb. But you're telling me x equals 0 or y equals 0. Damn, that's good. Yeah, that's a really good proof. That bugs me out. That bums me out. I spent like 20 minutes on it. Now, writing this verification is going to be annoying because I have to destruct cases. It's a union of any two intersecting lines. Want to show u plus v is not an A. Witness. Let u equal 0, 3. Let v equal 3, 0. 3, 3 is not in A. Because neither 3 equals 0 nor 3 equals 0. Scaling. Let u in A, let k in R. Want to show that ku is in A. Left. u1 equals 0 times k times k, k times u1 equals 0. Check. Right. u2 equals 0 times k, ku2 equals 0. Yeah. Right, I know. Like addition is really something. Like I'm thinking about. So it respects scaling, it doesn't respect addition. It's an interesting discussion point. I just gave like a linear algebra recitation because I tutor at a community college and we call them recitations. They're these like group sessions and there's no lecture this semester. It's an online course with no lecture. So like the tutoring groups are like the primary lectures, quote unquote. And like we had a long discussion about linear span today with students who had like no idea how to reason about linear span. Um, and I was just trying to. I think I did okay, but yeah, this is a good exercise to think about. All right, I spent a good 25 minutes on it though, so let's move on. We're showing that the periodic functions are a subspace. I think they. I'm just guessing they are a subspace. I haven't thought carefully about this yet at all. Um, but I just think the periodic functions are a subspace of R to R. Oh come on. Let FG in periodic R to R. Want to show that F plus G is in periodic R to R. Yeah, I'm really curious how this book is going to deal with bases and span. I mean, let me just look at the table of contents real quick and see when that is. Bases are in chapter 2, and span is in chapter 2. So we're doing that soon. So we know that there exists a K such that for all x, f of x plus k equals fx. And we know that there exists a J such that for all x, f of g of x plus j equals g of x. So is it too naive to say that, like, want to show there exists an L such that for all x, f plus g, x plus L equals f plus g of x? And is it too naive to say that, like, let L equal k plus j? So, f plus g of x plus k plus j. No, this is too naive. This is too naive. This isn't going to work. Equals, let's just say fx plus gx. X plus k plus j plus gx plus k plus j This does not follow. So it doesn't follow this way. But can I prove that I broke addition? I broke addition respecting this. See, that I'm not so sure about. I'm really not so sure about that. Why would the periodic functions form a vector space? I haven't thought carefully about this. I thought I would just dive into the algebra. Hold on a second. Yeah. There's certainly no proof that k equals j. Do y'all use let when you're instantiating an exists? Can you show us the question again? Sorry, I just saw that. A function f, r to r, is called periodic if there exists a positive number p such that f of x equals f of x plus p for all x in r. Is the set of periodic functions from R to R a subspace of R to the R? Explain. I'm thinking no, because I think I can clearly break. Like, the fact that I failed to derive doesn't mean that the derivation has failed. The fact that I failed to derive might just mean I haven't tried the right thing yet. But let's let k in R want to show that kf is in periodic R to R. So we know that we have a k in R such that f of x plus k for all x equals f of x. Oh, I'm using k too many times. P. Want to show there exists a q in R such that for all x, kf equals kf of x. Why shouldn't I be convinced that the q isn't just the p? Yeah. I mean, look at sine, for instance. The p for sine is 2 pi. And let q equal p. If k equals 0, then REFL, because that would just be 0 equals 0. Else, divide k by both sides and get f of x plus p equals f of x, which is true by hypothesis. And we're done. We're totally done. Well, we're done the scaling case. We need to show the addition case. And maybe the addition case won't hold. I mean, let's think. Sine plus cos of, let me just keep it, of theta plus 2 pi equals sine plus cos of theta. Plus cos theta plus 2 pi equals sine theta plus cos theta. Intuitively, we're going to make it work because sine plus cos is in the periodic functions from I guess, R to R. But the problem is, in the sine plus cos case, P equals Q, right? But in the general case, we have no such assumption. So I think it doesn't form a vector space. I think it doesn't form a vector space because in the general case, you would need P equal Q to make it form a vector space. Want to show that there exists an R in R such that for all x, f plus g, oh no, I'm out of room. And you can't show this. I think it's not a vector space. I think it's not a vector space. And you know what? Oh, come on. Fourier transform? What am I? Are the periodic functions a subspace of R to R? Yeah, they're saying it's not a vector space. Oh, wait, what's this? I want to spend some time reading this because my money is not a vector space. I don't really know what's going on in this proof right now. You think it should be a vector space? So let's think about series. I did not want to get into like heavy calculus. I am so not good at calculus, y'all. Oh, you know what? I'm not even going to delete any of this. I'm just going to scroll down. I can't scroll down that much. I can scroll down plenty. Yeah, let's not do. It's periodic with p times r. I didn't try p times r. Let r equal pq. Yeah, no, I don't want to mess with series. I just thought I might because if you help me through it, I might get somewhere with it, and it would be good to review. But like, I do not want to mess with series. I am not. I mean, do mathematicians even use this stuff? I feel like it's for engineers. Let r equal p times q. Yeah, we should try this, and it's about like the rationality of the period and everything. Um, case P, Q, and Q. There exists an AB such that P equals A over B and Q equals C over D. That doesn't help. There's a set of periodic functions from R to R, a subspace of R to the R. So I've seen a solution to this question. My question is, what are the thought processes to even think of sort of function to show that the set of periodic functions is not subspace? First, I do have a question what R to R would look like. I'm visualizing elements being some sort of infinite list of this sort. The main question, so the function chosen was. This isn't making sense. The way this person is setting it up is just not making sense. See, this isn't making sense either, because what they're not doing is they're not destructing out the periodic hypothesis to extract out the P and the... Like, where the heck does S even come from? The ratio of the periods of F and G must be irrational. So it's the ratio of the periods. Ratio of the periods. I have no notion of one of these things not being equal to 0. And I don't know... Well, any period being 0 is a degenerate case, because it's f of x equals f of x. So let's say that any period being 0 is not interesting. Declare that p equals 0 or q equals 0 is degenerate and not worth it. I think there's a trivial proof if one of the periods equals 0. P, Q, and N. So yeah, we don't necessarily have to show that. Yeah, exactly. That's why it's degenerate. That's why it's a degenerate case and should not have been counted. So what we need to do is we need to assume a periodic. We need to assume irrational to show that it's not a vector space. Because we're doing this for arbitrary periods in R. Consider the number P over Q. Case P over Q in Q. Then there exists AB in Z such that P over Q equals AB. Let R equal PB equal AQ. Then F plus G of X plus R equals F of X plus R plus G of X plus R. Since I cheated and looked it up, I have to go much harder in my execution. Equals F of X plus, it's still P times B. Plus G X plus AQ. Now, you can solve for A. You can replace A with BP times Q. BP divided by Q, but that's not going to work. Oh, but B is a, so this equals, because periodicity, X plus B, because B is an integer. Because B is an integer. Because periodicity. Boom! Rational case. So irrational. I mean, do you want me to show that it's irrational for P divided by Q is not in Q? Do you want me to show that it doesn't respect addition? Check. P over Q is not in Q. Wait, I already don't remember the scalar part. I remember. I don't even remember doing the scalar part. I feel like I did it a long time ago, like 20 minutes ago. Periods whose quotient is irrational is necessary. So P divided by Q is irrational. Which is, I mean, well, that's actually not the sine and cosine case. The sine and cosine case, because the pi's cancel. So 2 pi divided by 2 pi is 1. That's awesome. That's awesome that basically the rationally periodic functions. Well, no, I mean, not even that. If you have two functions whose quotient of their periods is rational, then they respect addition. But in general, this is not a vector space. Gerhard, do you agree that this is not a vector space? Because I'm not going to be able to find. I mean, like let's just call it. Let's just say that let R equal P over Q. Like I don't know, F plus G, X plus P over Q equals F of X plus P over Q plus G of X plus P over Q. This is a great exercise. I think I'm calling it on this exercise. What was it framed? Is the set of periodic functions for R or subspace of R to the R? Explain. It's not a subspace. It is not a subspace because it does not respect addition. All right, we're making progress. We're making progress. I'm going to move on to number 10 because I'm satisfied with number 9. I really am. I'm satisfied with number 9. I'm totally satisfied saying it's not a subspace. I totally believe it's not a subspace. Next song. Suppose U1 and U2 are subspaces of V. Prove that the intersection is also a subspace of V. Want to show that U1 intersect U2 is also subspace of V. let U1, let U and V be in. U1 intersect U2. And if the underlying field of V is F, then let K be in F. Want to show that U plus V is in U1 intersect U2. We also want to show that KU is in U1 intersect U2. So what we do is we split. Is in U1 and U plus V is in U2. Well, we split our hypothesis. UV is in U1, UV is in U2. This is true because U1 is a subspace of V. This is true because U2 is a subspace of V. All right, and then KU is in U1 and KU is in U2. True because U1 is a subspace. This one is a good candidate for formalization. I'm going to have to use ensembles and everything. All right, we're done. We're done with 10. That was easy. We're totally done with 10. It was totally easy. Oh, no, not this again. All right, we're going to scroll to the right now. Yeah, I want to do 11 too. I mean, this is the same. It's just some higher order programming. Like what you would do is you would every collection. I'm assuming finite collection is probably also true for intersection, but that's computationally a little bit more difficult. But you're just programming on like you're doing like a reduce. I think where you have hypotheses that everything in a list is a subspace, and you do reduce. I just want to skip this because I totally get the idea. Oh well, I'm not going to skip it. I'm gonna write it out. Oh, this is bad. For every A1 dot dot dot. You know what? We're just going to do it for every sequence. For every A function from... No, we're not going to do it like that because that makes infinite. Well, yeah, fuck it. We'll do the infinite case. Into the subspaces of V. So for every sequence of subspaces... Yeah, we're going to do this for sequences, not for collections. For every sequence of subspaces of V... AK is in subspaces V. Yeah, this is going to be a fun exercise. I'm glad I'm doing this one. I only have 50 more minutes, y'all. I can't work past 5 on this today, unfortunately. Today I have to stop at 5. I'd like to keep going, but maybe next week we'll do another 6-hour session, you know. But this week I'm going to stop at 5. Oh, by the way, everybody, I'm going to publish blog posts. Arc1.markdown. I'm publishing blog posts. Every 24 hours I stream, I publish a blog post. So I'm going to talk about everything we did so far. It's gonna be pretty cool. It's weird. Yeah, there we go. Want to show. So H1 is for all nat, for all k in nat, AK is in subspaces of V. And we can replace this. I'm trying to think of I'm thinking ahead to formalizing this. And I'm thinking ahead to how I would do that. And I'm going to try to do it for the infinite case. Like the infinite sequence case. And I'm already thinking in terms of cock constructs. I'm falling away from math and falling back into cock. But let's see. Yeah, I mean, I'll leave this up. Let UV be in the infinite intersection let K, I'm already using K, let P be in the field of V. Want to show that U plus V is in infinite intersection. Wait, did I do the previous part right? I can't. I already can't remember if I did the previous part right because I erased the previous part. No, wait. I think I did the previous part wrong. Oh well, I'll just continue. I think I did the previous part wrong. I think I made a grave error in the previous exercise. No, 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 no. I didn't make an error. Then, for every k in that, u and v are in ak. Because AK is in the subspaces of V, U plus V, and KU in AK. P. P, not K. 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 Math in public, y'all. I'm just having a good time here. That's what I'm doing. I'm basically done. I mean, I see it. I'm just figuring out how to write it. Because I did the sequences as a function of from. Let UV be in the infinite intersection of the AKs. Let P in the field of V. We want to show that PU and U plus V are in the infinite intersection of A plus K. Well, for every K, U and V are in the infinite are in AK, because that is a destruction of the intersection hypothesis, and because AK is in the subspaces of V, because A of K is a subspace, then U plus V and PU are in AK. So, for every K in N, U plus V and PU are in AK. Since A in the subspaces of V to the N was arbitrary, we have concluded that for all A in the subspaces of V to the N, K equals 0, intersect infinity, AK is in the subspaces. I'm satisfied with this, y'all. I'm totally satisfied with this. Let me just add one more thing. Yeah, I'm satisfied with this. This is great. I'm going to plug in my phone here. Oh, this is good. This is a good exercise. I'm glad I did it. I was going to skip it, but you know what? I'm going to return to it when I formalize, because this is an obvious candidate for formalization. Aha, the union of... So this goes back to the counterexample from exercise... From exercise 8. This is the counterexample from exercise 8. But now we're proving it. I might skip 13. Let U1, U2 in subspaces of V. Want to show that U1 union U2 is in the subspaces of V. If and only if I'm using this for if and only if right now. U1 is contained in U2 or U2 is contained in U1. Maybe I'll start writing with this. Nah. Though we could make it... I mean, I could have gotten rid of this thing the whole time. Could make it fine. Oh, that's nice. That's much nicer. Forward. Forward case. Suppose U1 union U2 is a subspace of V. I think the backward case is going to be easier, y'all. Backward. Suppose U1 is a subset of U2 or U2 is a subset of U1. Left. For every U in V, U in U1 implies U in U2. And for every UV in U1, I'll say U1 V1 in U1 for every K in F. U1 plus V1 is in U1, and KU1 is in U1. Do I have an item from U1? I don't have an item from U1. These are my premises. Want to show that for all U12, V12 in U1 union U2, and for all K and F, U12 plus V12 is in U1 union U2, and KU12 is in U1 union U2. That's the one to show. Oh, come on. For all U2, V2 in U2, for all K and F, U2 plus V2 is in U2, and KU2 is in U2. But we also have a hypothesis that being in U1 implies being in U2. So what that means is that U1 is in U2. And specifically, U1 plus V1 is in U2. And KU1 is in U2. I feel like I did this case. I feel like I'm done this case. I feel like I'm done this case, y'all. Because what you do is you destruct this want to show into for all U1 to V12, U1 well, no, it's like a yeah. This would be U12 plus V12 is in U1 or u12 plus v12 is in u2. And I could just pick one. But I've already got that one. That one's right here. Going back to pencil. Same for KU12. Right case similar. I'm done. I'm done with the backward case. I gotta do the forward case now. Oh, not this again. It's whenever I do control X. It's whenever I do cut. All right. Good stuff. Oh, I don't remember what I was doing. I was doing this. I deleted too much. I deleted too much. U1, U2 is in the subspaces of V. U1 union U2 is in the subspaces of V. If and only if U1 is contained in U2 or U2 is contained in U1. And I did the backwards case already, so now I have to do the forwards case. It's interesting. Like, I know what that X equals A or B means. X is in A or B means X in A or X in B. But I don't know what A union B in whatever equals. But it's probably not important. An elementhood statement with the subspaces relation, with the subspaces set, I mean, because he doesn't usually talk about subspaces set. Sorry, I'm kind of just cleaning up a little bit for some reason. All right. U1 union U2 is a subspace of V. Therefore, either the left or the right. All right. That means for every UV in U1 union U2, and for every K in F, U plus V is in U1 union U2, and KU is in U1 union U2. Want to show either U1 is included in U2 or U2 is included in U1. And we'll do this with case analysis. So addition. U plus V in U1 or U plus V in U2. Left. U plus V is in U1. I definitely have to get to the end of this before calling it a day today. U plus V in U1 or U plus V in U2. Okay, so I think u plus v and u1 since we're doing the left case, we're doing u plus v and u1. That's going to be it's either going to be this or this, right? So like it corresponds to left or right, um, left or right. The destructing of this or here is going to correspond to left or right of which thing gets proved. So only one of these needs to get proved, right, at a time. Um, so I think like I can't even decide though. This is a good candidate for formalization. I still don't know how I'm formalizing the subspaces, but you know, it's just going to be a record with an ensemble. It's just going to be a record with ensembles, y'all. I just might go straight inductive, you know. I don't know. I haven't decided yet. This is hard. Ah. Come on, it's been like 10 minutes. I've been stuck at this one spot for 10 minutes. And I feel like I'm running out of time because I only have another 10 minutes left before I gotta go because I have stuff I gotta do. So the problem is if I go left on the goal and I destruct this into for all W in V, W in U1 implies W in U2. The problem is I don't have a way of saying that W equals like U plus V. Oh, yes, I do. Yes, I do. Because what you do is you intros. In Coq terms, you intros. You intros these. If I call this H1, well, what I need to do is first say that, like, let W equal X plus Y, and then specialize sum X plus Y, that would be a lemma, and then specialize H1 at X, Y. So that would ultimately leave me with X plus Y in U1 is a hypothesis, but instead of the right, we're going to do the left. Instead of the left, we're going to do the right. And we're going to get U plus V equals X plus Y in U2, which is in fact the goal. Because we rewrote W as sum X plus Y. Because I believe this lemma is highly provable. For every V in V, there exists a UW such that V equals U plus W. I believe this is an incredibly provable goal. So let's clean up a bit. We have to do the left, but for the left would just correspond to right goal. So the left destruct, here, in fact, let me go blue. The left destruct, I'm using cock terms now, would correspond to the right goal. So I already did the backwards case like 20, 30 minutes ago. The forward case just got done for addition. I just need to do the forward case for scalar. So what the heck is going on? Scalar. And let me underline addition so it's clear what I'm talking about. KU want to show that KU is in U1 union U2. In other words, KU in U1 or KU in U2. No, I'm sorry. We have as a hypothesis. No, wait, we don't have to do anything else. We don't have to do anything else, actually. As a matter of fact, we don't have to do anything else. Because we only needed to show for addition because it's and in the context. And when there's an and in the context, you don't have an obligation to use both conjuncts. I don't have an obligation to use both conjuncts. I can if I want, but I'm not obliged to. So this is wrong. This is not the want to show. Have. KU in U1 or KU in U2. Let's do right goal, the right side of the goal. That's for every W in V, if W is in U2, then W is in U1. So pull that up to the top. So now we have a W in V, arbitrary, and we have a W in U2, hypothesis. So we can just get rid of W in V. And now we want to show W in U1. So lemma, for every V in V, there exists a K in F, and there exists a U in V, such that V equals KU. So W equals KU. We're not going to do KU, we're going to do PX. Specialize H1 at, for K do P and for V do X. So the hypothesis is that for every U in U1 union U2, for all K and F, KU is in U1 union U2. So if I specialize that hypothesis down to W, to X, and X is also in U1, is in U2, I mean. This got messy. This got really messy. It would be worth it to like turn this in. It's like the difference between like an in-class exam and a take-home exam, you know? Where like an in-class exam, like you can be a little messy because you don't have time to like start over in the middle of it and like rewrite it. But at a take-home exam, you're expected to like be super neat. The problem is I still have a destruction. This is my goal. I can prove it for the left, but now I can't prove it for the right. So my problem was I chose left goal versus right goal before I needed to do this further destructing. And I think that's a problem. But we should work that out when we formalize it, because I don't like to do a lot of heavy case analysis when I'm not in Coq. Like I want to use Coq to you know, do my case analysis for me. All right, y'all. I don't have time to do anything else. So yeah, this is going to be interesting. I might not prove a field containing two elements, which we did today in class. Well, but before I did this, I did a tutoring session, and we did Z2. Yeah, this is going to be hard. 13, I don't know. I literally might skip 13. What I might do is I might show that it's not true for the field with two elements, and I won't do it for the other cases because unions are just really bad to work with. But what does 138 look like? Oh, that's obvious. Yeah, I'll be able to do that really quickly. But I'm going to start with I kind of want to skip 13. So we got about halfway through this time. Almost halfway. We didn't actually get halfway. We didn't hit the halfway point. And we started at 4. So let's call it a third. We started at 4 and we got to 12. So that's 8. That's a third. That's exactly a third. So if next week I do a full 6 hours, I should get into the end. I should get to the end of this. But this week I can't because I have stuff to do. So I'll see everybody around. Thanks for coming to the stream.